Okay guys, so let's continue with our yesterday's discussion. Just a brief reminder, what we were doing, we were discussing variation of stresses within inflation. So in other words, we were saying that we know when a load is applied on a structure, it will deform. And okay, so if we apply a load on structure, it deforms, and deformation would mean that there will be tension and compressions in different region of a structure. Okay, and having tension and compression in different region means that you get stresses. So there are different variety of stresses within the structure. What we do is, for our convenience, we divide the whole structure into small boxes. Okay, and then we find out what stresses are in a box. Okay, so stress, as I told you, is dependent on two parameters. One is the direction of direction along the axis, and another one is the out of plane axis of the area, the reference area. So within a box, as you can see, so unlike vector is a quantity which has got three components. In order to define a vector, you need three components, isn't it? Okay, if you know the three components, you can define a vector, and then you need a direction. Okay, so vector has got three components along the three axes, if we are talking about 3D space. In case of stresses, we have, as I told you, 9 components. Okay, so stresses are taken based on are taken within a box. A vector is just a straight member which is located somewhere in a space. Okay, so it's just an arrow which is located in some space. That's the vector. The stress and every vector has got three components. In case of stresses, what we do is we get a box. Okay, and we say that there are three different types of stresses at each and every face of the box. Okay, so there are 6 faces, and we have got 3 stresses, so 6 3s are 18. So there are essentially 18 different stresses. Yeah, but due to equilibrium, that is summation of all the forces must be equal to 0, and summation of all the moments, okay, that must be equal to 0. We break it down to 9 components. Okay, and you can see 9 components appearing over here. All the other components, they are equal to the stresses which you can see in this sketch. Okay, so the stresses which are on the other faces, okay, they will be equal to the stresses which are on this face. Okay, so we have got 9 distinct stresses. Okay, and if you know these 9 stresses, then that means that you know the stresses appearing on each and every face of this 3D element, which is a cube element. Now, what happens is that in this course, we are not talking about 3D. We are talking about only 2D. So the 2D means that you are just looking at a particular direction and you get a 2D box which looks like this one. So we have eliminated the third direction, which is this one. All the forces which are on this plane and the plane behind, okay, those are omitted. In other words, if this is your XY, okay, so you are looking at this from the top. Okay, so it's only the faces whose stresses are relevant. The other stresses they are irrelevant for us. So we are talking about 2D structure. So we take this element. This element is essentially the element which you get when you are looking at this box from the top. Okay, and we are trying to find out the maximum stress occurring at particular plane within this element. So this is one set of stresses. Okay, this is one set of stresses which appear on this box, or in 2D case which appears on these faces. Okay, it's one set of stress, but we don't know whether this is the maximum stress. What we are interested in is the maximum stress. Why? Because we designed our structure based on maximum stress. We need to know how much maximum stress can run into a structure so that we design it accordingly and it doesn't collapse, or it doesn't break. So that's why we, within this element, we take another reference plane, okay, and we try to find out the stresses on that plane. So we have these orthogonal planes. We take just a random plane, and that plane is located at an angle theta. Okay, so what we are saying is that look at the breakdown of the structure. This is the whole structure. We break it down into small boxes, which is this one. Now we are actually simplifying our concept. Okay, so from a 3D space, 3D structure where there is stresses within that structure, we are trying to make our understanding more coherent, more conceptual, okay, and more ordered. So we have this 3D structure. This 3D structure, we assume that is made up of lots of infinite boxes, okay. Each box at every face has got some stress, okay, and that is shown over here. So this is the 3D box of this, but then we further simplify it, okay. We say that we will just consider 2D stresses. In other words, the stress in the z direction we don't consider. We just consider the stresses which are in the xy direction. So essentially we are looking at this box from the top, and we say that we are not concerned with the z's. Every stress which has got z appearing, that we omit, remembering that our convention of stress is not the sign convention. The way we understand our stress is that we put two subscripts. We assign two subscripts to it. The first subscript is actually telling us the direction of that stress, and the second subscript is actually telling us the phase we are interested in. Okay, the phase, the outward drawn normal of that phase. So the phase is, for example, this one. The outward drawn normal is in y direction. That's why you have got y appearing in the second seat of your subscript. Okay, at the front seat you have x appearing. So x means that its direction is in the x direction. Okay, the front seat has got is telling you the direction of the stress. The back seat is telling you the direction of outward drawn normal of that phase. So that is then brought over here. 2D element is brought over here, and now what we want to do is, we know these stresses, and these stresses, I told you that you can determine it in a lab. Okay, from a lab test you can determine the stresses, the stresses within a particular box. Okay, so if this is your structure, you can put your strain gauge anywhere. Okay, in the horizontal direction and in the vertical direction. One in the vertical, one in the horizontal. So the strain gauge with either expand or it will compress. Okay, and it will give you certain value of strain. Yes. So that strain, when you multiply it with E, you would already know the E of this structure. So it can be steel, it can be rubber, it can be wood, anything, and you know the stress, you know the modulus of elasticity. You multiply that with E, the strain, and you get these values. Okay, so the stress you would know, the strain you would know. The stress you would know from the strain which you determine from the lab tests. And once these are known, once this is known, then you would have this element known essentially. Now you want to find out what is the maximum stress. Okay, what's the maximum stress which this element can take? Okay, no, what is applied onto this element? So the maximum stress can be at any inclination. Okay, it can be at any inclination. So what we say is that we take another plane which is at an angle theta. Okay, and we try to find out the maximum stress at this plane. So, and at this plane we have got normal stress and we have got the tangential stress.